In 2033, somewhere over a city like this, a school bus-sized object traveling 17,500 miles per hour could tear through the atmosphere and crash back to Earth. We don't know where. We can't precisely steer it, and unless something changes, we may not be able to stop it. That object is the Hubble Space Telescope. For 35 years, Hubble has orbited silently above us, circling the planet every 90 minutes, 16 times a day, more than 200,000 orbits since 1990. Each pass capturing light that began its journey billions of years ago, each orbit revealing something no human being had ever seen before. It helped us measure the age of the universe with remarkable precision, 13.8 billion years, a number that reshaped modern cosmology. And in one single image, the Hubble Deep Field, it revealed more than 3,000 galaxies in a patch of sky no larger than a grain of sand held at arm's length. 3,000 galaxies. In what we once thought was empty darkness, that is what is falling. But while Hubble has been staring outward, gravity has been working inward. Even hundreds of kilometers above Earth, a thin trace of atmosphere lingers. When Hubble hits it at 17,500 miles per hour, it feels drag. Drag steals speed. Lower orbit means more drag. More drag means a faster descent. It's subtle, but it never stops. During the first 2 decades of its mission, astronauts fought that descent. 5 separate servicing missions brought crews face-to-face with the telescope. They corrected its flawed mirror, replaced aging gyroscopes, installed new instruments that made it more powerful than its original designers imagined. Astronaut Story Musgrave floated beside Hubble in 1993 and later said, "This will outlive me. This matters more than I do." In those moments, the Space Shuttle's thrusters gently boosted Hubble into a higher orbit, buying it years of life, years of discovery, years of images that would hang in classrooms, museums, and on the walls of children who dreamed of becoming scientists. But the final servicing mission ended in 2009. The Space Shuttle program retired in 2011. The ability to physically reach Hubble vanished. The original plan had been simple. At the end of its mission, astronauts would retrieve the telescope and bring it home safely. No one expected it to outlive the spacecraft built to save it. Now there are no routine boosts, no scheduled rescue flights. NASA modeled the decay of Hubble's orbit under different solar conditions. When the sun grows more active, it heats and expands Earth's upper atmosphere, increasing drag on satellites. A quiet solar cycle could slow the fall. A violent one could accelerate it. Best case, Hubble survives until around 2040. Worst case, Reentry begins as early as 2029. The most probable estimate centers on 2033. That's 2,920 days away. Before that date arrives, Hubble will circle Earth roughly 47,000 more times. 47,000 laps. 47,000 chances for gravity to pull a little harder. And here's the problem. Hubble was never designed for a controlled reentry. It has no propulsion system capable of guiding itself safely into a remote stretch of ocean. When it falls, it will fall uncontrolled. As it plunges downward, atmospheric friction will superheat the structure. Much of it will disintegrate. But engineers calculated that several dense components could survive. Metal assemblies, reaction wheels, structural beams. Those fragments could scatter across a debris corridor, stretching hundreds of miles. Where exactly that corridor appears depends on timing, solar activity, and Earth's rotation at the moment of breakup. A shift of minutes could move the path across oceans or across cities. Along its usual orbital inclination, projections for a 2033 reentry show a casualty risk of roughly 1 in 330. That's about the same statistical likelihood as being struck by lightning in your lifetime. Except lightning doesn't arrive as a multi-ton spacecraft scattering debris over an urban skyline. NASA's internal safety threshold requires risk to remain below 1 in 10,000. By that standard, Hubble does not meet the requirement. In Singapore, directly beneath part of Hubble's orbital path, a student once asked during a public discussion, "What if it lands here?" The room went silent. No one had an answer. Inside NASA, the silence feels heavier. One NASA engineer told me privately, "I've spent 15 years keeping Hubble alive. I don't want my last act to be calculating where it kills someone." That's the tension. Hubble is not just hardware. It's one of the most beloved scientific instruments in history. It cost more than $10 billion across its lifetime. It redefined astronomy. It revealed supermassive black holes at the centers of galaxies. It mapped the distribution of dark matter across cosmic scales. It helped confirm that the expansion of the universe is accelerating. And yet physics does not care about legacy. Right now, as you're watching this, Hubble has already dropped a little lower than it was yesterday. NASA is studying options. A robotic mission could attach a propulsion module and boost Hubble into a safer orbit. Another possibility is guiding it into a controlled descent over the ocean. Each solution carries cost, engineering risk, and political complexity, and the clock is ticking. 2029 is only a few years away. 2033 is less than a decade. Before we watch it fall, we need to understand what we truly stand to lose, because Hubble is still working, still capturing light from the edge of the observable universe, still sending back data that challenges our understanding of how everything ends. And recently, Hubble photographed something NASA did not expect to find. Something that could change what we think about the ultimate fate of the cosmos. We have less than a decade to study it before Hubble burns. For decades, Hubble has done something no human eye ever could. It looked back in time. Every image it sends us is history. Light doesn't travel instantly. It moves at 186,000 miles per second, fast enough to circle Earth 7 times in 1 second. Yet even that speed isn't enough to erase distance. When Hubble photographs the Andromeda Galaxy, we see it as it was 2.5 million years ago, long before humans built cities, before recorded history, before modern civilization even existed. When it stares deeper toward galaxies billions of light years away, it shows us light that began traveling before Earth had oceans. Hubble isn't just a telescope, it's a time machine. That's why its position above Earth's atmosphere matters so much. On the ground, telescopes must look through layers of air that blur and distort light. Turbulence makes stars twinkle. Ozone blocks most ultraviolet radiation. Moisture bends wavelengths out of shape. Up there, Hubble sees clearly. No flicker, no atmospheric shimmer, no interference. Just raw, unfiltered light from the edge of existence. And that clarity changed everything. In the 1990s, astronomers pointed Hubble toward a tiny, seemingly empty patch of sky. It was a risky decision. Some scientists worried they were wasting precious observing time. Days passed as the telescope gathered faint photons from what appeared to be darkness. When the data came back, it stunned the world. The image, later known as the Hubble Deep Field, revealed thousands of galaxies crammed into a region of space, no larger than a grain of sand held at arm's length. Each galaxy containing billions of stars, each star possibly surrounded by planets. It was the moment humanity realized the universe was far more crowded and far more ancient than we ever imagined, and Hubble kept going. It discovered 2 additional moons orbiting Pluto, Nix and Hydra, expanding our understanding of that distant dwarf world. It found that nearly every major galaxy contains a supermassive black hole at its center, not rare anomalies, not cosmic accidents, a rule of structure itself. It captured direct evidence that galaxies collide and merge over time, that cosmic violence is normal, that the Milky Way itself is on a collision course with Andromeda. It mapped dark matter in 3 dimensions, not by seeing it, because it's invisible, but by measuring how its gravity bends light from distant galaxies behind it. The result was the first large-scale observational map of the invisible scaffolding holding the universe together. Before that, dark matter lived mostly inside computer simulations. After Hubble, it lived in observation. The map revealed something eerie. Dark matter isn't spread evenly. It forms a vast cosmic web, long filaments stretching across millions of light years. Where those filaments intersect, galaxies cluster. Where the web is thin, space is nearly empty. Over billions of years, gravity pulled those filaments tighter, clump by clump, shaping the structure of everything we see. And then there was dark energy. By studying distant exploding stars, supernovae so bright they outshine entire galaxies, Hubble helped confirm that cosmic expansion isn't slowing down, it's speeding up. Something is pushing the universe apart. We still don't know what it is, but without Hubble, we wouldn't even know it existed. It also detected water vapor in the atmospheres of exoplanets, spotted organic molecules in distant planetary systems, captured ultraviolet images of newborn planets forming around young stars, found evidence of water plumes erupting from Europa, one of Jupiter's moons. Each discovery was a first precise measurement of the universe's expansion rate, first detailed look at planetary building blocks around other stars, first surface image of a star beyond our sun. And it did all of this with technology designed in the 1970s. That's the extraordinary part. Hubble wasn't supposed to last this long. It survived because humans kept saving it, servicing it, upgrading it, believing in it. Now that era is ending. As newer observatories like the James Webb Space Telescope take their place, some assume Hubble's job is done. It is. Webb sees primarily in infrared. Hubble sees in visible and ultraviolet light. Together, they form a complementary pair, one looking at heat and the earliest galaxies, the other capturing the brilliant visible structures of cosmic evolution. When both observe the same object, scientists can combine their data to create a more complete picture. If Hubble falls uncontrolled in 2033, that partnership ends, and there's something else. Hubble has been quietly observing a mystery that could redefine the fate of the universe itself. For years, measurements of the universe's expansion rate have produced a growing discrepancy. The number calculated from nearby galaxies doesn't perfectly match the number inferred from the early universe. The difference may sound small, a few kilometers per second per megaparsec. But in cosmology, small differences become enormous over billions of years. Some physicists now call it the Hubble tension. If the discrepancy is real, it could mean our current model of physics is incomplete. It could hint at unknown particles, new forces, or revisions to our understanding of dark energy. And Hubble's data sits at the center of that debate. Which means the telescope that may soon fall from the sky could also be holding clues about how the universe ends. That's the paradox. Above us, a machine built to explore infinity is running out of time. Below it, a planet full of people debates whether to save it, guide it down, or let gravity decide its fate. Because intervening isn't simple, attaching a propulsion system to Hubble would require a complex robotic mission, precision docking, autonomous navigation, significant funding approval, and time. Every orbit without intervention brings it closer. By 2033, if nothing changes, Hubble will enter its final descent. Metal will glow, panels will fragment. Pieces will streak across the sky like artificial meteors. Somewhere on Earth, people may look up and see a brilliant fireball, unaware they're watching the end of one of humanity's greatest scientific achievements. But before that happens, Hubble may deliver one last revelation. Because its latest observations suggest something unexpected about the expansion of the universe, something that doesn't fit neatly into our current equations. If confirmed, it could reshape our understanding of cosmic destiny. And if Hubble burns before we solve it, we may lose the instrument best suited to answer the question. Gravity is pulling Hubble down, but the real question isn't just where it will land. It's whether we'll solve the universe's biggest mystery before the telescope that revealed it disappears forever. At 17,500 miles per hour, Hubble will slam into the atmosphere. No steering. No second chances. The descent will begin quietly. A slight dip in altitude, increased atmospheric drag. Then, within minutes, friction will ignite the outer structure. Temperatures will spike. Panels will tear away. The telescope that once floated in silence will become a streak of fire across the sky. From the ground, it may look like a meteor storm. Bright fragments scattering across darkness, phones lifted, videos recorded, headlines breaking in real time, but this won't be a natural object. It will be 35 years of engineering, science, and history coming apart in flames. Most of the structure will disintegrate under extreme heat. That much is expected. The real uncertainty is timing. The exact second of breakup determines everything: the debris corridor, the geography below, the difference between ocean and city. And that uncertainty is what keeps NASA running the numbers. At NASA's Orbital Debris Office in Houston, engineers load updated solar forecasts into atmospheric density models. They run the simulation, and again, the answer shifts slightly each time. Solar activity rises, the projected reentry moves earlier. Solar activity dips, the timeline stretches. But one conclusion remains unchanged. Without intervention, Hubble will come down. The question now is whether to act before that happens. A controlled rescue mission is technically possible. A robotic spacecraft could rendezvous with Hubble, dock autonomously, and attach a propulsion module. That module could either raise Hubble into a safer orbit, buying another decade of science, or guide it into a controlled descent over a remote region of ocean. Estimated cost: between $300 and $500 million. For comparison, that's roughly the price of building 2 modern NFL stadiums, to save the most important telescope humanity has ever launched. Some argue it's a bargain, others call it unnecessary. The James Webb Space Telescope has already taken over the spotlight. Its images dominate headlines. Its infrared mirror peers deeper into cosmic history than Hubble ever could. But Webb did not replace Hubble. Webb sees primarily infrared. Hubble sees visible and ultraviolet light. Lose one, and half the spectrum goes dark. Certain measurements, particularly those tied to galaxy evolution and the ongoing Hubble tension in expansion rates, rely on Hubble's wavelength precision. Without it, some questions stall. Inside NASA, 2 camps quietly formed. One senior engineer reportedly said, "We can't let it fall." Another responded just as bluntly, "We can't afford not to." Both are right in different ways. Funding a rescue means pulling resources from future missions. Not funding it means accepting a statistical risk that technically exceeds internal safety thresholds. Meanwhile, gravity continues its work. If the current projections hold, 2033 is the likely year of reentry. That's fewer than 3,000 days away. Roughly 47,000 more orbits. And every single one lowers Hubble just a little more. March 2033, global tracking networks lock onto Hubble's final descent. News channels run countdown graphics. Governments under its orbital path issue advisories. Social media fills with live skywatch streams. Mission control watches telemetry flicker across screens. Altitude dropping, velocity holding. Thermal stress rising. Then plasma begins to form around the spacecraft as it hits thicker layers of atmosphere. Communications degrade, signals fragment, and finally, the data stops. The telescope that measured the expansion of the universe goes silent. If debris falls harmlessly into the ocean, the event becomes a dramatic but safe farewell, a fiery ending to a legendary mission. If fragments land elsewhere, investigations begin. Questions follow. Could it have been prevented? Should it have been? That uncertainty is what makes the next few years critical. Several private aerospace firms have already proposed attaching a boost vehicle to Hubble. One concept involves launching a spacecraft capable of autonomous docking, gripping Hubble's structure and firing thrusters to lift it higher. Another plan would guide it into a precisely targeted oceanic reentry zone, eliminating risk to populated regions. The engineering is challenging but achievable. The timeline is tight but not impossible. The decision is political. And while committees debate and budgets circulate through Congress, Hubble continues its work. It still sends back images, still gathers ultraviolet data Webb cannot, still refines measurements of distant supernovae, data that feeds directly into one of the biggest mysteries in physics: why the universe's expansion rate doesn't quite add up. That discrepancy, known informally as the Hubble tension, may require several more years of observation to resolve, years that depend on keeping the telescope operational and stable. If reentry accelerates toward 2029, that window narrows sharply. If it holds until 2033, there is time, but not much margin. Every orbit now carries two meanings: scientific opportunity and physical descent. There is something haunting about that duality. Above us, a machine built to study infinity is constrained by the thinnest edge of our atmosphere. A telescope that showed us galaxies billions of light years away may meet its end within a few thousand miles of home. And the choice of how that story ends no longer belongs to physics alone. It belongs to us. Hubble showed us the universe. Now we decide, do we save it or let it burn? It is not failing, it is still working. Hubble continues to orbit Earth every 90 minutes, locking onto distant galaxies, tracking ultraviolet flares from newborn stars, and measuring supernova explosion that refine the expansion rate of the universe. Its gyroscopes stabilize its aim. Its instruments transmit data with precision that engineers in the 1970s could only hope for. This is not a dead satellite drifting toward Earth. It is an active observatory with unfinished work. The telescope is still delivering publishable science. In the last few years alone, Hubble has tightened measurements of distant supernovae data that feeds directly into one of the most unsettling problems in modern cosmology: the mismatch in the universe's expansion rate. Early universe measurements suggest one value. Observations of nearby galaxies suggest another. The gap is small on paper. Over billions of years, it becomes enormous. If that discrepancy holds, it could signal new physics, a shift in our understanding of dark energy, a revision to the model that explains how everything evolves. Hubble sits at the center of that debate, and yet its orbit continues to decay. A rescue mission would not just reduce ground risk, it could extend Hubble's life another 5 to 10 years. That extension might be enough to resolve the expansion rate mystery with higher confidence. The estimated cost, $300 to $500 million. For context, that's roughly the price of 2 modern NFL stadiums. Inside NASA, the discussion is no longer theoretical. One camp argues that Hubble is still scientifically valuable and deserves a boost to a safer orbit. Another argues that every dollar spent on an aging telescope is a dollar not spent on future missions, planetary defense systems, Mars exploration, next-generation observatories. Gravity doesn't wait for budget approvals. Meanwhile, the James Webb Space Telescope continues operating from deep space. It replaced Hubble in headlines, but not in capability. Webb sees primarily infrared light. Hubble sees visible and ultraviolet wavelengths. Lose one, and half the spectrum goes dark. Certain measurements cannot simply be transferred. Some long-term observation programs rely on decades of continuous Hubble data. Interrupt that timeline and comparisons become harder. If no mission intervenes, the final phase will unfold quickly. Engineers will narrow the reentry window as atmospheric drag increases. Solar forecasts will tighten predictions. Governments beneath the orbital path will prepare contingency plans. March 2033. Tracking stations lock onto Hubble's descending orbit. News networks run countdowns. Aerospace analysts explain breakup dynamics in real time. In mission control, telemetry streams across monitors. Altitude decreasing, surface temperature rising, structural stress climbing. Then the plasma blackout begins. As Hubble tears into thicker atmosphere, ionized gases surround it, disrupting radio signals. Data flickers, then stops. From the ground, observers see a bright arc splitting across the sky. Fragments burn, trails fade. If debris lands harmlessly in open ocean, the world exhales. The story becomes a dramatic but controlled farewell to a historic instrument. If fragments fall elsewhere, investigations begin immediately. Could it have been boosted? Should funding have come sooner? Was the risk truly acceptable? Those questions will be asked either way. Hubble's legacy, however, is already measurable. It helped determine the age of the universe, 13.8 billion years. It revealed that cosmic expansion is accelerating. It mapped the large-scale structure of dark matter across space. 3 discoveries that permanently altered astrophysics. That record will not burn up in the atmosphere. But the opportunity for more discoveries might. If Hubble remains operational through 2033, it still has roughly 47,000 orbits left. Tens of thousands of passes over Earth. Tens of thousands of chances to capture new data. The timeline is shrinking. A robotic boost mission is technically feasible. Aerospace companies have outlined docking systems capable of autonomous rendezvous. Propulsion modules could either raise Hubble into a higher, safer orbit or guide it into a precisely controlled ocean reentry. The technology exists. The decision remains. Because this is no longer about whether Hubble was successful. It is about whether we extend the life of a working observatory or allow it to descend naturally and accept the risk. The final years will define how this story is remembered, as a controlled transition into history or as a countdown watched by the entire world. Hubble showed us the universe. Do we lift it higher or let it burn?